Welcome to this last video in my main Dark Souls 2 physics breakdown. For this one, we'll look over rotational or circular motion. This can be applied to a sword swinging through an arc, for example. When dealing with circular motion, it's much simpler to account for angles of a circle first. For a sword swing, this would include finding values such as the angle the sword moved through, commonly represented by theta, and how quickly it moved through that angle, which is known as angular velocity and represented by omega. Then we can convert those angular values to linear distances, velocities, and so on. Angles of a circle can be measured in degrees, or more commonly in units of radians, with 2 pi radians being the angle sweeping all the way around a circle. In Dark Souls 2, many weapons are based on real-life medieval weapons, with most being reasonable for a person to use. But Dark Souls 2 also features some incredible weaponry that would take unreal strength to lift, let alone wield. For our rotational motion analysis, I'd like to draw our attention to the most exaggerated melee weapon in the game, the Smelter Hammer. True to form, the player displays extreme effort in every swing of this solid lump of iron. One move in particular is a whirling spin attack, which ends by carrying the player off their feet before landing face first on the ground. As ridiculous as this seems already, physics can tell us how much more ridiculous it really is. To begin, we need to find out the dimensions and mass of the Smelter Hammer. Remember the tiled plaza from the horizontal motion video? It also serves as a great spot to measure the hammer with. By placing the Smelter Hammer parallel to the ground, we see it's 11 tiles long, with each tile being 2.29 centimeters. This makes the hammer 2.52 meters or 8.27 feet long. Then, measuring a picture from the side gives its widest width to be about 2/7 of its length. Although the hammer isn't exactly circular, we'll approximate it as such to make the math easier. Since the handle is about 1/5 of the hammer's length, we'll also ignore it when calculating the volume. This will avoid including a lot of empty space that wouldn't contribute to the mass anyway. Now we can break down the hammer into 2 parts, the top being a hemisphere, and the rest down to the handle as a cone. Taking the radius of both the cone and hemisphere as 1/7 of the hammer's length, that will leave the cone with a height of 23/35 of the hammer's length. We can find the hemisphere's volume through 2/3 pi times r cubed, with r as the hemisphere's radius. We can find the cone's volume through 1/3 pi r squared times h. Adding the volumes together gives a total volume of 0.324 cubic meters. That doesn't seem like much right now, but then we multiply it by the density of iron to get the mass. Iron has a density of 7,860 kilograms per meter cubed, so that gives us a mass of 2,550 kilograms or 5,620 pounds. That's over 2.5 tons, more than an average car. Going back to the spin move footage, we see the player can swing this melted down car at high speeds before getting carried off the ground. Let's find out how fast the hammer was going before launch. Here we see the hammer swings through a full rotation in an average of 0.356 seconds. We get the angular velocity as follows. First, take the angle traveled, theta, divided by the time t it took to do so. In this case, the hammer moved through 2 pi radians in 0.356 seconds, meaning an angular velocity omega of 17.7 radians per second. Well, how does that help us? We can then convert this angular velocity into linear velocity to find out how fast the hammer is going at any particular moment, and how fast it would hit something. To convert angular velocity omega to linear velocity v, we multiply the angular velocity by the distance from the rotation point at the center of the circle to the hammer's center of mass, which is represented by r. I took r as approximately 3/4 of the hammer's length due to the hammer's elongated teardrop shape. Plugging in these values gives us a linear velocity of 33.4 meters per second, or nearly 75 miles per hour. Wow, it really is like the player's wielding a car. But wait, there's more! If we find the centripetal acceleration, we can then find the force required to hold onto the smelter hammer during these spins. As a brief background, centripetal force is what keeps an object spinning in a circle rather than flying off. In our case, it's the amount of force required to hold onto the smelter hammer and keep it moving in a circle rather than letting go and, say, demolishing a nearby wall. Centripetal acceleration refers to how quickly the object is turning. As such, it depends on the linear velocity of the object and its distance from the center of the circle. The faster it's going, the more turns and the higher the acceleration. The farther away it is, the slower it turns and the lower its acceleration. Centripetal acceleration is found with the equation AC equals v squared over r, with v being the object's linear velocity and r being the distance of its center of mass from the circle's center. We can calculate centripetal force with force equals mass times acceleration, plugging in the centripetal acceleration AC for A. Plugging in the velocity, center of mass distance, r from earlier, and the hammer's mass, we see that it takes 1.5 million newtons, or 338,000 pounds of force to hold on to this thing. No wonder it sends the player flying. After taking this closer look at Dark Souls 2, I'm impressed to see the care the developers took in making many aspects of the game's physics believable while still fitting them into a fantasy setting. But I'm also impressed by how unrealistic things could get when the developers wanted to have a little fun. Taking the time to examine this game using physics revealed more about this incredible world than I thought possible from a regular user's perspective. And yet, using physics, we found that the player's basic movements are very close to realistic for humans in many cases. We also found the heights of several monumental structures, and how amazing a feat wielding the smelter hammer is. That's one of the great powers of physics, being able to take data about the world, analyze it, and make predictions with math that help us understand how the world works even better. Thank you so much for watching. If you enjoyed this video, and especially if you'd like to see more analysis of video games using physics, math, and whatever cleverness I can come up with, please like and subscribe. Thanks again, and see you next time.